so let's say x scales like epsilon to some power. I mean, let's assume for the moment that x scales like epsilon. It's not necessary, but x very, very small. And when x very, very small, we are solving in a different manner. And the point is that we are going to consider the overlap region. And the way we are going to determine the coefficients is to require this solution, the inner solutions, and the other solution to overlap in the overlap region. So it's like what you did in quantum mechanics when you have a potential well. You calculate things by or otherwise piecewise potential. You solve it with patching, right? What is patching? לתפור תנאי שפה. You have solution here, you have solution here, and you want the psi and the first derivative of psi to be equal at the boundary. Now we are doing matching. It's not patching, but matching. And the difference is that there is a region over which we expect the two solutions to be the same. Not a point, but a region. Okay. So how do we do that here? First of all, we can write y out. Now, y out, if you y out is just taking epsilon to be 0. Right? So for y out, we have y prime. Okay, we take the outer regime. We take epsilon to 0, where y prime plus y is 0. Right? Which implies that y is a e to the minus x. Right? This is a solution for this equation. And now we have to determine A. In order to determine A, we should have to determine A through the boundary conditions. Which of them? This one. Why this one? Because y out is out. Yes. Now, why I didn't choose y out to be in this direction and y in to be, I mean, that's a good question. We will explain it later. So how did I know to choose y out in this side and to y in that side and not vice versa? We will discuss it later on. So we want the boundary condition y of 1 is 1, and this requires A. So if x is 1, we have e to the minus 1. So A must be e. Right? So y, at the end of the day, y out is e to the 1 minus x. See? Now, what about the inner regime? In the inner regime, we are doing, I did all that in the last lecture, but I just want to remind you. In the inner regime, we define x tilde to be x over epsilon. Why? Because I say that in the inner regime, x is order epsilon, x is very small. Again, why I'm choosing epsilon and not square root of the epsilon? This is an issue that we will discuss later on in this lecture. But let's flow with me, right? Let's take x to be x tilde to be x over epsilon. Meaning that, what is our logic? Our logic is that in the inner regime, x is very small, but x tilde is order 1. So we want to change the scaling such that we will work with not a number which is order 1. Now, because x tilde is order 1, and now we are doing a change of, we are changing this equation and for y of x tilde. So we know that every derivative, right, d dx is actually 1 over epsilon d dx tilde, and we change all the derivatives here. So we get epsilon over epsilon squared y double prime, where now prime is derivative with respect to x tilde. Right? Plus 1 plus epsilon over epsilon y prime plus y equal 0. Right? So we have 4 terms here, and now let's multiply everything by epsilon. in order to make the y double prime. Again, now prime is with respect to x tilde, very important. So we multiply everything by epsilon and we get y double prime plus y prime plus epsilon y prime plus y equals 0. Okay? I simply took this as two terms. Okay? And now I am neglecting this because we are in the inner regime. Epsilon is small. And we find that in the outer regime, in the inner regime, y double prime plus y prime is 0. So what's the solution? So we can write y prime e to the x prime equals 0 because this is integrating factor, right? So y prime e to the x is a constant. So y prime is a constant e to the minus x. So y is a constant e to the minus x plus another constant c2. Again, I don't care about the minuses and the integrations because it's a constant, so, right? But in any case, now, in order to have a solution, we should solve for the two constants. How do we do that? We have, first of all, we have the boundary condition. What is the boundary condition now? Y of 0, y in of 0 is 0. By the way, note that this is x tilde. Right? Everything here is a function of x tilde. But since x tilde is x over epsilon, when x goes to 0, when x is 0, x tilde is also 0. Right? Which implies that we want C1 plus C2 to be 0. So C2 must be minus C1. So this should be C1, 1 minus e to the minus x tilde. That's the solution. This satisfies the boundary conditions. Because x tilde goes to 0, everything goes to 0. Okay? So we have somebody who is trying to... So all in all, we have y out is e to the 1 minus x, y in is c times 1 minus e to the minus, and let's write it explicitly, x over epsilon, because x over epsilon is x tilde. Okay? Now we have to determine c. We cannot determine c with the left boundary condition, because, I mean, this solution satisfies y in of 0 is 0. This solution satisfied y out of 1 is 1. Okay? Now the question is, what is c? So to determine c, we have to match this condition and this condition. Where? In the overlap zone. What's happened in the overlap zone? The overlap zone is x much smaller than 1, but much larger than epsilon. So what can we say in this overlap zone? Right. On the one hand, x is much larger than epsilon, so we can use the outer solution. On the other hand, x is much smaller than 1, so we can use the inner solution. You see? So we have a zone, a region where both solutions should hold. Right? And in this solution, they must match. So I'm taking by implementing x much smaller than 1 to the outer solution, I will get that in this regime, right? In this regime, x is much smaller than 1, so I have e in the overlap regions, right? On the other hand, if I'm implementing, so I'm implementing here the x much smaller than 1, and I'm implementing here the x much larger than epsilon, then this term is 0. You see x tilde is going to infinity. This term is 0. and we get that x, y in is C. So it must be that C is E. This completes the solution. So we must have C equals E. And then we can write what we called in the last lecture uniform approximation. So Y uniform is Y in plus Y out minus the overlap. So it will be e to the 1 minus x plus e minus e to the 1 minus x over epsilon. You see I just put here, plug in here C equals C, and multiply that, minus e, which is the overlap. Because in the overlap regime we are counting it twice. The e and the e goes away, and we have e to the 1 minus x minus e to the 1 minus x over epsilon. This is our approximation, uniform approximation. And note that this approximation satisfies the left boundary condition, because when x goes to 0, we have e minus e. But the right approximation, if I'm taking x equals 1, then this will be 1 minus e to the 1 minus 1 over epsilon. So as epsilon goes to 0, this will be 0. Right? So I have the uniform approximation misses the right boundary, the outer boundary condition, but only by a factor of e to the minus 1 over epsilon, and this factor is going to 0 as epsilon goes to infinity. Okay. Questions so far? Yes?
Why we can neglect these terms order of epsilon?
Okay. Thank you very much. Another question? Okay. So I'm returning to your question. So we can now, this was first order approximation.
Okay.
This was first order approximation. Now, if we want higher order approximation, then we can say, for y, let's say y, what about y out, right? In y out, we assume that epsilon is, this is the equation in the outer regime, and epsilon is small, and all other terms are order 1. All other terms are order 1, right? So we can write, for y out, we can write the zeroth order approximation was y prime plus y is 0. Right? This was the zeroth order approximation that yields this solution. So this solution is a solution to the zeroth order. Right? What is the solution? So this is the solution for epsilon to the 0. For epsilon to the 1, if we plug it there, we are going to have, we have 4 terms, right? But epsilon is 1. Okay, so I'm collecting terms. Oh, sorry. I'm doing it too fast. Sorry. No. I'm doing it too fast. This is not. Okay. Start at the outer regime. Okay? We write y out as sum from n equals 0 to infinity of y out n times epsilon to the power of n. Perturbation theory, right? First order, zeroth order approximation. So from now on, I'm not writing y out. Zeroth order approximation, y prime plus y equals 0. First order approximation. What is a first order approximation? I'm plugging this into that equation and collecting terms of order epsilon. What will be the first order approximation? Right? If I'm multiplying something by epsilon, it should be y0. Because y1 will have an epsilon in front of it, so it will be epsilon squared. So what I will have here is y0 double prime plus y0 prime plus y1 prime plus y1 equals 0. And epsilon squared, we will have y1 double prime plus y1 prime plus y2 double prime plus, prime plus y2 equals 0, and so on.
Which is the same thing as the previous one.
Yes. Each one depends on the previous one, right?
Yes,
This is
but
in
it's
the outer
literally the
regime.
same.
Actually, we discovered that y0 satisfies that, right? Right? Which implies that this is also 0.
Yeah.
So we have here an homogeneous equation for y1
Which is
with a non-homogeneous part is 0. Right? This is a given part. This is a non-homogeneous part, and so on and so forth. So actually, 0 is a solution for all the higher terms. So y out is e to the 1 minus x is a solution to all orders in perturbation theory. Right? Now, what about the inner solution? So, if you remember, in the inner regime, we have y double prime plus y prime plus epsilon y prime plus y is 0, where now y is a function of x tilde, not of x. Of x tilde. Okay? So again, we can write y in is sum from n equals 0 to infinity of y in n times epsilon to the power of n. And we will, we had an epsilon also here. Right? And we collect term by term in epsilon. So we are going to find that y0 double prime plus y0 prime is 0. This was the equation that we have calculated before. And the next equation will be, this is to the power of e to the, and the epsilon equation will be y1 double prime plus y1 prime equals to, plus y0 prime plus y0 equals 0, and so on and so forth.
where did the y1 double prime came from?
From here, we plug this into that equation.
Yes, but you don't have epsilon y double prime. It's y1.
That's exactly why, right? And so on and so forth. We are going to get solutions here, right? Every time we have this will behave like the inhomogeneous part of this equation because we know it from the first, and so on and so forth. And we have to match them. Okay, I'm not going to do the work, but here you get some different solution for any order in epsilon. Now, how you match it to this thing? Right? Very nicely, because you can write this y out as e to the minus e to the 1 minus epsilon x tilde, because x tilde is x over epsilon, and then write it as e times 1 minus epsilon x tilde plus epsilon squared x tilde squared over 2, and so on and so on, and then you match this to that order by order. Okay? It's not important, I'm not going to do that, but just to explain you that what we are doing here through this lecture is the first step in a perturbation theory that you can do to any order, right? Fine.
So inner solution is also the same for all.
No. The fact that the outer solution was have no perturbative correction, this fact is the peculiarity of this problem. There is no, it's not a general thing. In general, you will have here solutions and here solutions, and you have to match them order by order. Right? Yeah. But okay, again, this is not so important. It's just to show you that essentially you can implement this technique to get higher order corrections. Good. So again, as I said, all this problem is solvable. It is just for its value is just as a demonstration. It has no practical importance. However, now we are going to do something which is very important practically, and this is to solve we want to solve every second order differential equation. Okay, there is no such a thing, right? But we can get solution for every homogeneous second order differential equation where in the limit epsilon goes to 0. Right? So let's write the most general second order differential equation is that. Do you agree with that? What?
For homogeneous.
This is the most general equation. Okay? Second order homogeneous differential, linear differential equation. This is the most general case. To solve that is nobody knows. Right? We know many special cases. We have Airy function, we have Bessel function, we have cylindrical function, we have Laguerre functions, we have blah blah blah, we have blah blah blah. But the most nobody knows how to solve the most general second differential equation. Okay? However, if we are lucky enough and the coefficient of the highest order thing is small, then we can approximate the solution, an approximation that becomes exact as epsilon, more and more accurate as epsilon goes to 0. Right? So once you are adding this epsilon, you can get solutions that will be true if epsilon is small, and if not, you can develop the perturbation theory and try to get to larger and larger values of that epsilon the way we demonstrated before. Okay, so we have the equation is between, as I defined it, between 0 and 1. Of course, this is completely arbitrary, between 0 and 1. And now again, I want you to trust me about two assumptions that I'm going to do. First of all, let me first of all define that, because this, you see, this is completely general. So the question is, what is the first question? That if I want to treat it using this technique, using boundary layer technique, the first question is which boundary I will solve, I will define the inner and which one will be the outer. A question that you were able to ask me before, as I already pointed out, but right, so I'm now doing two assumptions, and later on you will understand that they are connected to each other. First of all, I am assuming that a of x is larger than 0 for all x between 0 and 1. So a of x do not change its sign between 0 and 1. And second, I will choose this to be the inner and this to be the outer. And I'm telling you in advance that we will find that if a of x is smaller than 0, then we should invert our choice.
And if it changes sign?
If it changes sign, then you commit suicide. No, but you have to do something more complicated, right? But if it does not change sign and it's always positive, it turns out that this should be the inner and this should be the outer. Right? That's the rule. Okay. So once we have that, we can continue. What's happening in the inner solution? So now let's say, starting with the outer. Outer solution is simply taking epsilon to 0. In the outer regime, we have the license to take epsilon to 0 because the y is not fluctuating enough, strong enough to compensate for the epsilon which is small, right? And we take epsilon to 0, so we find out y prime is minus b of x over a of x y. This is an exact equation, no problem, we can solve it. We can write dy over y is minus b of x over a of x dx, and we integrate both sides. We get ln y is the integral up to x of b of t over a of t dt plus a constant. So y is some constant, let's call it c, e to the minus, I need more, y is constant e to the minus the integral up to x of b of t over a of t dt. This is the solution in the outer region. Now we have to satisfy the outer boundary condition, which is what?
B.
What?
Then it's
That at 1 it will be b, right? So how do I do that? The simplest way of doing it is to write this garbage as b times e to the minus, or to the plus, sorry, the integral from x to 1 of b of t over a of t dt. Clearly, this is a solution. Because as x goes to 1, the exponent is 0, and we have simply b. Right? So this is the outer solution that we obtain this way. Okay? That's the outer solution. What about the inner solution? So we have to in the inner regime, if you remember, we define x tilde as x over epsilon. So every derivative gets 1 over epsilon. So what we are going to get is epsilon over epsilon squared y double prime plus a of x y prime divided by epsilon plus b of x y equals to 0, where now y is y of x tilde. Okay? Good. So we have two terms that are, okay, let's multiply everything by epsilon, and we have y double prime plus a of x y prime plus epsilon b of x y is 0, and to the zeroth order we are going to neglect this term. Because now this term is proportional to epsilon and this term is small. Still, we have a very difficult equation. Because now we have a second order. For example, if a of x is x, we have, it's not a, but I mean it's garbage. Okay? However, now we can improve because we know that x tilde x, the x is very small in the inner region. x is very close to 0. Okay, x is very close to 0, not x tilde. If x is very close to 0, we can take a of x to be simply a0. So in the inner regime, we have x tilde is x over epsilon, and our equation is y double prime plus a naught y equals 0. A naught y prime. Right? So we write it as y prime e to the minus a naught x tilde prime equals 0. So y prime is some constant, let's call it C1 e to the a naught x tilde. I mean, this is constant. No, I have a plus. So plus, yes. Right? So this is a minus. And y, again, is C1 e to the minus a naught x tilde plus C2.
A naught, it's a of x, then x equals 0.
Hmm?
A naught, it's a of x.
A naught
x,
is a
equals
naught.
0.
A of x equals 0.
Ah.
I call a naught. Sorry for not spelling this out.
You multiplied by e to the a naught x in the first step.
Yes. It's an integration factor. Now, okay. Now the situation is as follows. I have the inner solution. I have the outer solution. Right? And I have to match them. Where do I match them? As I say, the outer solution is fine as long as x much larger than epsilon. That's a condition for the outer solution to be fine, because we know that the y double prime is getting out of control only in the epsilon vicinity of 0. Okay, and we know that this is the outer solution regime. The inner solution regime is fine as long as x is much smaller than 1. Okay, so in this overlap regime, we want both solutions to be right. So so y out, when we take x to be much smaller than 1, what we are going to get? We are going to get b e to the minus e to the integral, sorry, from 0 to 1 of b of t over a of t dt. Let's call this q, just because it will appear many times and I don't want to write it again and again. Right? What about the inner solution? Y in at x much larger than epsilon. What does it mean, x much larger than epsilon? It means that x tilde is going to infinity. If x tilde is going to infinity, this term cancels out and we get C2. So this will approach C2. So my condition for matching is C2 equals Q. Okay, so I've forgotten to satisfy the left boundary condition. The inner should satisfy y in at x tilde equals 0 must be a, right? And so in order to do that, it should be right. Sorry. So y in is C1 times 1 minus e to the minus a naught x tilde plus a. Clearly it satisfies the left boundary conditions. condition. And now if we take x tilde to infinity, meaning x is much larger than epsilon, then this goes away, and we find that C1, we have C1 plus A, this will approach C1 plus A. Yes? And this should be Q. So this ends the story, so it determines C1 to be Q minus A.
You still didn't match the right. You did.
No, this is a matching. I satisfy the left boundary conditions, I satisfy the right boundary condition, and this is a matching, and because of that I can write the uniform solution as what? As y out, which is b e to the y out is b e to the integral from x to 1 of b of t divided by a of t dt plus the inner solution, and we decide that C1 is Q minus A. And so we have Q minus A times 1, and now we have minus Q minus A times e to the minus A naught x over epsilon. I trade x tilde for x over epsilon. And we have plus A. And we have to also to subtract the value at the matching regime, because we counted it twice.
The uniform is in all the.
Uniform is inner plus outer minus
But
right?
But
This
it's
is
relevant from x
y
to 0
in
to 1.
plus y out minus y match.
And it's relevant from 0 to 1?
Yes, yes. So we have y. This was y out. This was y in, right? And we have to subtract the match, which is to subtract q, right? Minus q, which is a match. And now you see that this a goes with this a, and this q goes with this q, and we ended up with okay, we can cancel this and cancel that, and that's it, right? Only make the minus, right? This minus. That's right. Minus q minus a e to the minus a naught x over epsilon. Okay? Now, what's happened when x goes to 0? If x goes to 0, sorry, what's happened when x goes to 0? Yes. When, wait. This is q. You see? When x goes to 0, this is 1. Okay? And the q will cancel that, because when x goes to 0, this goes to q. Right? So we are going to get A, as advertised. Okay? And when x goes to 1, this, the integrand goes to 0. So we get B. And x over epsilon is so huge when epsilon goes to 0, if x is 1, so this term cancels out and we get B. Okay? Again, there is a slight mismatch, because if epsilon is 10, then we have here something like e to the 1. Sorry, if epsilon is 0.1, we will have here something that looks like e to the minus 1, e to the minus 10, but this is only a slight mismatch. Okay. Good. So this is, by this way, we can solve every second order differential equation, linear differential equation, provided that we have epsilon in front of the highest derivative. Now, let's go back to the condition A goes to 0. First of all, you asked me why. First of all, what happened if A crosses 0 somewhere?
We know how to solve the equation in this point.
What will happen if we take A
You divide by
that
0.
crosses zeros? Oh, good, very good. In this term, when A crosses 0, this blows up. So the technique as we put it, get bankrupt if A crosses 0. So it will work only when A is either completely positive or completely negative in the regime we are interested in. Okay, now another point. Note that if A is always positive, then A0 is also positive, because A0 is just the value of A at x equals 0. It was written here somewhere, right? x0, A0 by definition is A at x equals 0, and it will be positive. Right. What will happen if A will be negative? Suppose that A do not cross 0, but at x between 0 and 1, A is negative. What will happen then?
The integral will be negative.
Okay. What will happen if A, right? This was our condition. We convinced ourselves that if A crosses 0, then we have the explosion of the integral, and there is no way of doing anything.
We need to switch the inner and outer because
Exactly. Thank you very much. If A of x is below 0, then A naught will be negative. Now, if A naught was negative, this will be e to the 5. Let's say A naught is minus 5. We have e to the 5x tilde. When we want to match, we match when x tilde goes to infinity. We will have infinite. We have no chance of matching it. And therefore, we have to switch the boundaries. So if A of x is larger than 0, we have to take this as the left boundary as the inner solution, and this one as the outer solution. If A of x is smaller than 0, we have to take this solution, this as the outer solution, and this as the inner solution. Very important. Okay. Good. So, this was again the general solution to every every linear differential equation. Okay. Now, we were left, except of doing examples, we were left with 2 points that we don't know how to accommodate with. One of them is what's happened, what we are doing, what we're supposed to do when A crosses 0. Right? Another point is what I told you, that I have chosen x tilde to be x over epsilon. Why not x over square root of epsilon, or x over epsilon squared, or anything else, right? So, as I told you, this epsilon is the width of the regime, right? Close to the inner solution, where the y double prime is getting out of control and is changing so much that the second derivative of it is order epsilon. But who knows? Maybe the second derivative is order square root of epsilon or order epsilon squared. Everything like that will go to 0 as epsilon goes to 0. Right? So what is the width of what is the actual width of the region where we should implement the y in and where we should implement the y out? Okay. To understand that, let's consider the following let's consider we can continue with this equation. So we continue with this equation, which is completely generic of course. But now let's do that in a more careful way. More careful. I will not assume that the inner regime is of width epsilon. I assume that it is of width delta. Right? And now I'm introducing a new small parameter, delta. And so I will define x tilde to be x over delta. And every derivative with respect to x is 1 over delta, the derivative with respect to x tilde. And now I'm going to rewrite this equation. And rewriting this equation, I will have epsilon over delta squared y double prime. Again, y double prime is the derivative with respect to that. Plus a over delta y prime. Plus b of x y equals 0. So I'm doing exactly the same, except that I do not assume that the width of the inner regime is actually epsilon. I am taking, this is called distinguished limits. We have to decide what's the width of the inner regime. How we are doing this decision? So first of all, one thing is still true, that delta is going to 0. Right? Delta is very small. Otherwise, it's not a boundary layer. It's right? Delta should go to 0 as epsilon goes to 0. In some manner. Right? Maybe it's square root of epsilon, maybe it's epsilon squared, but in some manner it should go to 0. Okay? And because it goes to 0, the x tilde, sorry, this is not x. This is a of actually, okay. So this is A0 and this is B0. This is still good approximation. Right? Because we are dealing with a region around the 0 such that I can safely replace A and B by their 0 value. Okay? And now let's multiply everything by delta squared over epsilon just to be on the safe side. So we have y double prime plus what? Plus A0 times, what do I have here? Times delta over epsilon y prime plus B naught delta squared over epsilon y equals 0. Okay? Now, remember what we actually did when we dealt with this equation. We did assume that delta is going like epsilon. Right? If delta is going like epsilon, then this term is order 1, this term is order 1, this term is order epsilon, and we can throw it away. And this gave us a good solution. Right? What will happen if I assume that delta is much bigger than epsilon? Say, because epsilon is going to 0, let's assume that delta goes like the square root of epsilon.
Then y tagain nila.
Okay? If delta is going like square root of epsilon, then what I will have here is y double prime plus a naught divided by square root of epsilon y prime plus b naught y equals 0. Right? You see? Because this is 0. So this is epsilon. Right? So now I can clearly, this term will dominate the system when epsilon goes to 0. And what I will get is that y prime is 0, in which case I cannot match anything. Right? That's a problem. Again, what I did here. Okay. Yes, I will get a constant that I cannot match. The other possibility is to take delta, say, epsilon squared. Delta is going like epsilon squared, say, right? In which case, what will happen? If delta is epsilon squared, much smaller than epsilon, right? Then I will get y double prime plus a naught times epsilon y prime, right? Which is negligible, plus epsilon b naught y equals 0. This term and this term are negligible. So I've gotten y double prime is 0. If y double prime is 0, then y is a plus b x tilde. And again, this is not going to constant as x tilde goes to infinity. So we will have no matching. So the only way to get a matching is to choose delta equals epsilon. Right? Or at least delta proportional to epsilon. You can choose delta equals to 5 epsilon, but not something that... so this is what is called the distinguished limit. The distinguished limit is the case where delta is equal to epsilon. And this distinguished limit is actually the width of the boundary layer, right? The width of the boundary layer, we have seen that there is a boundary here, right? The width of the boundary layer will be epsilon. The smaller epsilon is, the smaller the width of the boundary layer. Okay, so in order to understand better this idea, let's take an example in which the distinguished limit is not epsilon.
If in the distinguished limit you don't have a matching overlap, because on one hand x is the order epsilon, the other hand x needs to be much larger than epsilon.
Again?
In the overlap, in the distinguished limit,
Yes.
on the one hand x should be order epsilon, and on the other hand...
No, in the overlap, x tilde is infinite. Because x tilde is x over epsilon. So it must be the case that the solution of the... okay, so... I have to supply... I have to supply the boundary conditions. The boundary conditions are y of 0 equals y of 1 equals 0. Okay? Why this is ugly?
Because there is no difference between inner and outer solution.
No. It is ugly because there is no a naught. A naught is the limit of the coefficient of y as x goes to 0. But now there is no a naught. Right? So let's make the analysis. We assume that y is, we assume x tilde to be x over delta, and now we have to decide how delta should behave as a function of epsilon. Okay? We plug it in, we get the epsilon over delta squared y double prime minus, okay, what will be this term? Note that we have to write everything in terms of x tilde. Right? This is the inner equation, and the inner equation should be written completely in terms of x tilde. So we have here x squared is what? Is delta squared x tilde squared times y prime divided by delta. And now we have minus 1. Right? This is the inner equation. And now we multiply, in order to free the y double prime, we multiply everything by epsilon, by delta squared over epsilon. And we get y double prime minus delta cubed x tilde squared y prime over epsilon minus delta squared over epsilon times y equals 0.
So just y double prime is David.
Okay, now the question is how to choose delta. So suppose we are doing what we did until now. Until now, what was our policy? Choosing delta equals epsilon. If delta equals epsilon, then this term is epsilon squared. This term is epsilon. So we have only y double prime equals 0. And y double prime equals 0, we know the solution is a plus bx tilde and we cannot match it. Right? So there should be something else. What we should do, we should try all the options. So we decided that delta equals epsilon is not good. So either delta is much larger than epsilon or delta much bigger, much smaller. Right? The inverse of larger, smaller. Yes. So, okay, so let's for example think about the case where delta is square root of epsilon. If delta is square root of epsilon, what I have here is y double prime minus this is square root of epsilon x tilde squared y prime minus if delta sorry yes no okay sorry I want delta to be, let's try delta equals epsilon squared. Okay? If delta is epsilon squared, I have y double prime minus, oh no. So I have epsilon to the 5, x tilde squared y double y prime minus epsilon cubed y equals 0. Clearly this is 0 and this is 0. So we have y double prime equals 0, it's not good. Because again, we have something that cannot match. So let's try delta square root of epsilon. And if I'm trying delta square root of epsilon, what I will get is y double prime minus square root of epsilon x tilde squared y prime minus y. That's good. Why that's good? Because this implies that we can neglect this. So now the distinguished limit is delta equals square root of epsilon. This will be the width of the boundary layer. The boundary layer will be much wider than the boundary layer in the former example. And what is the solution of this fantastic equation? What? Yes, exactly. So y is a e to the x tilde plus b e to the minus x tilde. It's not harmonic oscillator. It's inverted harmonic oscillator. Of course, we should take this. We should throw this one because otherwise it will never match when x tilde goes to infinity, right? And with this one, we have to satisfy the inner boundary condition. The inner boundary condition is y of 0 is 0, which implies that, what? No, y of, what's going on here? Oh no. So I simply copy the wrong number. Sorry. Which implies that b equals 1. Right? So y in is e to the minus x tilde, which is e to the minus x over what?
Square root of epsilon.
Great. Square root. Good. Now, what about y out? So what we are doing to get y out? Simply throwing the terms that are proportional to epsilon. Right? That's so what we are doing with y out will satisfy y prime is equal to minus y over x squared. Do you agree with me? I simply forget about this term. So dy over y is minus dx over x squared. So ln y is minus 1 over x, minus ln y is minus 1 over x. Y minus.
No, it should.
Maybe, wait. Do I have a sign mistake here? Oh.
I think you should neglect the e to the minus r.
No, it's fine. That's a solution without the minus, right? So y plus the constant, of course. So y out is e is some constant, c, times e to the 1 over x. Yes.
In the inner part, doesn't x tilde goes to infinity?
What?
In the inner part, x tilde doesn't go to infinity?
No, in the inner part, x tilde is order 1. It's going to 0 when x goes to 0, and in general, it's order 1.
So why can you neglect the a e to the x tilde?
I must do that because I know that the matching will, in the matching regime, if x tilde goes to infinity. And because of that, if a is not 0, this term will explode and I will not be able to match it to anything on x. Okay? Now,
And why couldn't you neglect the constant?
what?
Why could you neglect the constant in the y inner part?
In the, which one?
In the y inner part, shouldn't you have b e to the minus x tilde?
Yes, but now I want y of
Okay.
0 to be 1. So when x tilde is 0, this should be 1, so b is 1. That's next time. Okay, so this is y out, but now the question is, what happens? So y out is supposed to satisfy this boundary condition. The y of 1 is 1. However, this is not correct. Although it seems that you can do that, right? It is not true. Okay, and I should not call it y out. I'm calling it y middle.
Why?
Just give me some credit, right? Not me. Give the book some credit. I would stop here and just match it to the. But if you read the book, you see that now we have to analyze separately the regime which is very close to 1. So how we analyze separately the regime very close to 1? Here we assume that x tilde is x over epsilon, x over delta. Very close to 1, right? Very close to 1, we should assume that we define z as 1 minus x over delta. Okay? If this is z, then d dx is d dz is still d dz 1 over delta. Okay? And if you plug it here,
Isn't it minus 1 over delta?
what?
Isn't the dx minus 1 over delta? You said because minus
Yes. Yes, minus. Right. Now the chain rule. Very good. And plugging it there, we have epsilon over delta squared. The two minuses are plus, right? Y double prime minus. Okay. Now x, now we can approximate x by 1. Right? Because we are close to 1, not close to 0. So we have 1 over delta y prime minus y equals 0, where again y now is a function of z. And now the distinguished limit is delta is like epsilon as before. You can it's exactly the same considerations that we did before, because the point is that this is not proportional to delta, and what we get is we can multiply everything by epsilon, and we get y double prime minus y prime. Wait. This is plus because of this your minus, right? Plus y prime minus epsilon y is 0, and we throw this one to 0th order in epsilon, and what we will get is y prime e to the z prime is 0, because this is z, right? So y prime e to the z is a constant, so y, let's call it another k. So y is k e to the minus z, this is y prime, so y is k1 e to the minus z plus k2. Now we have to satisfy the right boundary condition, which is 1. So we want this at z equals 0, yes, when x equals 1, z equals 0. We want this to be 1 when z is equal to 0, which implies that k1 plus k2 is 1. So we have 1 plus 1, k1 plus k2 is 1, so k2 is 1 minus k1, so we have k1 times 1 minus e to the minus z plus 1. Good. So we have 3 regimes, right? And now we have to match them. Remember? Okay. So we have 3 regimes. The inner one, in which y in is e to the minus x over square root of epsilon. The middle one, in which we have c e to the 1 over x, and we don't know what c is, because we have no boundaries for the middle. And the outer, for which y is k times 1 minus e to the minus 1 minus x over epsilon, which is z, right? Plus 1. Now we should match them. How do we match every neighboring pair? So when x is much larger than 1, but much larger than the square root of epsilon, but still x is much smaller than 1, right? Then this will be e to the minus infinity, which is 0, and this will be, right, so this will give 0, and this, when x is much smaller than 1, what it will give me? It will give me c e to the 1 over x, so it diverges. So I have no other choice but deciding that c is equal to 0, right? So this gives me c e to the 1 over x, which goes to infinity. So there is no other choice but taking c to 0. And now I can ask what's happened when x is going to 1. So this will be 0. And this when x goes to 1, this when 1 minus x is much larger than epsilon, this cancels out, and we have k plus 1, this goes to k plus 1, and if k plus 1 is equal to 0, it implies that k is equal to minus 1.
If x goes to 1, then 1 minus x is much larger than epsilon? If x goes to 1, 1 minus x goes to
In
0.
any case, c is 0, so you don't care.
No,
in this stage, you decided that c is 0.
No, you talk about the y out. You said that when x goes to 1, 1 minus x over epsilon is much.
No, not
much
actually. When 1 minus x is much larger than epsilon. It's like saying that x is much larger than the square root of epsilon.
Ah, okay.
Right? So this is 1 minus x much larger than epsilon. That's a condition. So z goes to infinity, if you want. And then you get here k plus 1, which should be 0, so k is minus 1. So we have, all in all, y in is e to the minus x over epsilon, y middle is 0, and y out is, because k is minus 1, this cancels with that, so it gave us e to the minus 1 minus x over epsilon.
E to the minus x over square root of epsilon in the y.
Over square root of epsilon, yes. So all in all, the y uniform is e to the minus x over square root of epsilon plus e to the minus 1 minus x over epsilon, and I have nothing to subtract because the boundaries are 0.
So it's basically 0 until you reach the
Yes,
very end?
yes. So the way it looks like, if this is 0 and this is 1, right, and this is 1, so what it is doing is exponential decrease, 0, and exponential increase. And the smaller epsilon is this regime and this regime shrinking. However, this regime is proportional to epsilon and this regime proportional to the square root of epsilon. So this one will be infinitely larger than this one in the limit epsilon goes to 0. Good. Finally, okay, so there is one point that I left behind. I explained everything, I think, except of the point that what we are doing when a of x crosses 0. Okay? Good. Now, as a final example, I would like to show you how to implement the boundary layer theory to nonlinear differential equation. Right? How to implement the boundary layer theory to nonlinear differential equation. So let's look at the following garbage. Epsilon y double prime plus 2y prime plus e to the y equals 0, where y of 0 equals y of 1 equals 0. Good. So you see the horror in this story. We have e to the y, not e to the x. If it was e to the x, it was an equation with constant, inhomogeneous equation with constant coefficient, and we can solve it very easily. But if we have e to the y, that's infinite order nonlinear equation. Okay? So first of all, let's ask what's happening in the outer regime. What does it mean outer? We just take this to be 0. Bye-bye. Right? And what we get is 2y prime is equal to minus e to the y. So e to the minus y dy is minus 2dx. I mean, this is an exact equation because it's first order. Right? I can integrate both sides. From this I will get minus e to the minus y. Yes? And this equals to, this is 1/2, of course. Okay, and this is minus x over 2 plus a constant. Yes. Yes? Am I right?
Yes.
So e to the minus y is is x over 2 minus a plus c, who cares, right? C is a constant. So what is y? Y will be minus the logarithm of x over 2 plus c. Right? Note that, because this is nonlinear, the constant is not out here, but inside the logarithm. Now, we have to satisfy the boundary condition. If I want now y of 1 equals 1, this implies that I want, this may be written as,
Zero, not 1.
y of 1 equals 0. This implies that x over 2 plus c must be 1, not 0.
How
Right?
do we know that we don't?
But x is 1, so c should be 1/2.
How do we know that we don't need to do all this again, like the mid and outer?
We don't know. I mean, we have no drawings for it. So c is 1/2, and what we have is y equals to minus ln of x over 2 plus 1/2, which is ln of 2 divided by 1 plus x. Okay, that's the outer section. What about the inner? So for the inner, again, we are doing our standard trick, and we assume that x tilde is x over epsilon, so we assume that the distinguished limit is epsilon and not anything else because we have no time. And we plug it here, so we get epsilon, 1 over epsilon. Am I right? Yes. Okay. So we get 1 over epsilon y double prime plus 2 over epsilon y prime plus e to the y equals 0. Multiplying it by y, note the miracle, we get y double prime plus 2y prime equals 0 because this term is now going with epsilon. Right? So we throw this term when as epsilon goes to 0. We throw this term and we get what? We get so y prime e to the 2x tilde prime is 0, and therefore y prime is some a e to the minus 2x tilde plus b. But we want that when x tilde is 0, we want y to be 0. So it must be the case that we have here a times 1 minus e to the minus 2x tilde. Up to renaming the constant. Or instead of the x tilde, I can write x over epsilon. Good. Now the matching. Okay? When x is much larger than epsilon, this goes away and we have a. On the other hand, the outer solution, when x is much smaller than 1, then we have ln 2. Therefore, a is equal to ln 2. Right? So the inner solution is ln 2 times 1 minus e to the minus 2x over epsilon. The outer solution is ln of 2 over 1 plus x, right? And the uniform solution will be this plus that minus ln 2, minus a match. So we are going to have the uniform will be ln of 2 over 1 plus x minus ln 2 times e to the minus 2x over epsilon. So you see that at x going to 0, I have ln 2, and here I have ln 2, so ln 2 minus ln 2 is 0. Fine. When x is going to 1, then I have here, this is 0. And this will not be 0, but it will go like e to the minus 2 over epsilon, that is negligible as epsilon is becoming very small. So this is a mismatch of the uniform solution. Good. So, today what we have shown you is how to implement the boundary layer technique. As you have seen, there are many, you can read a lot about it in the book. You can, I didn't touch two things. One of them, higher order analysis in epsilon. So we did it in the first example that was quite trivial. Even there we didn't do that seriously, but just show in principle how to do that. This is one thing that I did Khafif. Second one is a case when a of x crosses 0 in the between the left boundary and the right boundary. We will regard to that tomorrow, or in our discussion of the WKB techniques that I will start tomorrow. And there are also all kind of pilpulim about the distinguished limit in all cases, and systems with infinite number of distinguished limits, and internal boundary layers, which is what happens when A crosses 0, and so on and so forth. We cannot cover anything, but the technique is very important and very useful, right? You have many times in which the coefficient of the highest derivative is small parameter, and in each of these cases you can use the boundary value technique. Thank you very much.
Thank you.
And see you tomorrow.
So the last example was about that we can implement such technique even if
even in nonlinear equations.
Yes.
Why it was so important to me to show you that? Because tomorrow I will teach WKB. Now, for linear equations, WKB may be used instead of boundary layer theory. So they are they are the same. You can just use WKB, but in nonlinear equations, WKB is both.
בת ה-18 פלוס, אתה בא איתי? אני לא הולך לבד. תומלין זמן כזה. גם בטח לא מצחיק בלייב, זה בטח כזה מעייף. טוב, אז אתה בא בינתיים? אל תלך לכל שאתה נוטש אותה. אני אחרי זה אלך למדמחיסט. עד היום היחיד שאני פה בשלישי. למדמחיסטים. ליה, רעות. אין דבר כזה שיעורים בשיטות. צריך לעבודה. אין דבר כזה, זה נגמר בתרגיל אחד. זה נגמר בתרגיל אחד.
כאילו מה זה? אתה יכול לפתוח רק מבפנים.
הבנתי.
מעצבן.
לא. רגע. מה הוא עשה פה? מפחד שהוא עושה את הדוגמאות שלי. זה המדר מסדר ראשון?
לא.
מה המדר פה?
בצד שמאל למטה, בכחול. כי
בצד-
למטה, בצד שמאל. כן. פשוט מדר לא לינאר.
לא אחי, הוא גנב לי את אחת הדוגמאות.
כן, הוא אמר שזה מהספר גם.
כן, אני לקחתי מהתרגול של שנה שעברה, הוא לקח לי דוגמה של... רגע, זה... זה המדר לא ליניארי, הוא לא עשה לכם מדר מסדר ראשון, boundary layers על מדר מסדר
יכול
ראשון.
להיות שהוא עשה בשעה הראשונה שלא הייתי פה. In the first hour of the lecture, did he wrote a first order linear equation? Or it was always second?
It were...
No.
I don't think it were linear
Only second
equation,
order.
but it were first order OD.
No.
He didn't... That is the only example he did?
No.
No, we did
No,
another
not
example,
only
but
this.
it was second order, right?
Yes. Yes.
Okay, nice,
Only
because
this,
I just...
second order.
I just want to present an example. My example is specifically made for the case when your uniform is not just a constant; it's a function by itself. Because I will show you. Okay, so and I will show and present some.
You
And
mean uniform solution?
there
Or
is
solution in the
inner plus outer
Yes.
minus
Minus
uniform, a matched
Yes.
solution. I mean the match function.
This is. You mean this is. You want to show the example where it's
Yeah,
not
I
constant?
will show it. I will show it. We'll
Oh.
just go to the bathroom quick, and then there were more people. I don't think so.
Only Nimrod and Shai. they left.
Very good. Very good. Very good. Nice student. I will go to the bathroom, and then we will start and finish soon. Okay. So let's start quick and finish earlier. It's okay?
Yes.
Okay, so one thing that I want to mention about problems like this one, that you in next lecture you will see WKB, that intuitively it's like doing e to the s with specific assumptions. I don't know how Nadav will present it, but it has some sort of boundary layer spirit, but not not that much. But it's practically doing e to the s. Why, for example, for this case, you can do e to the s? It's non-linear differential equation, right? That's why, if you remember in the first tutorial, I told you, okay, oh no, if it's not linear, there is a couple of things that you can do, but practically that, I think that is the only method you can apply it with simple, without getting too much into calculations for non-linear equations. Okay? That is what I want you to remember, and WKB will not work here. But what you can actually brute force and try to do assuming y is sum of delta to the n y n from n equal to 0 to whatever, okay? And then what you get, you can actually approximate e to dy with orders of delta, right? Yes? And that is a method that you can try to do perturbation theory with, because you will get that as a sum of all blah 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 deltas, and then you will get what you want. But it's the best shot that you can do to apply any other method. Besides that, I don't think there is any other thing, and I'm pretty sure that boundary layers is better. But when you will try to take more terms in boundary layers, did Schnell try to do it?
Yeah.
Yeah, but only to one example, right?
Yes.
What he did, he took to the inner solution sum like this, and for the outer solution and matched them also, right?
No.
No? What he did?
He just briefly mentioned how we're supposed to do it, not explicitly write things.
What he did? More specifically?
Just said that we can plug not epsilon equals 0, but go and find another terms.
Yeah, more terms, and then you
Yes.
get, and then match them,
Yes,
right?
yes.
Exactly. That's what I want to talk about, because when you do that, there are some stuff that you need to be careful about. For zeroth order, they might not affect your solution, but for higher orders, it will definitely affect them. By the way, for this tutorial, I'm using the notes from last time, okay, which we didn't finish. One of them that was one of the problem, and the second problem, which I will solve, what I told you before the tutorial, and couple of examples, and something that is more like extra. It's not specifically for the course. It's very important, so you will know that. But it's not likely to appear on the test, but it could be. I don't know. It appeared once, something like that, and Nadav specifically wrote what to do in those cases. It's good to see in class, but it will likely not appear in tests, so I just want you to not freak out if it seems complicated. You should know that and understand that to the test, but it's not the end of the world. Okay? That is one. That is the one before my last tutorial to the next 5 years, right? I'm going to the military for 5 years, so I will not be able to get money, so I will not work for free, right? So
in the military, you are working for free. I don't know what.
yeah. Okay,
You are working there for free.
except that thing, yeah. Only for the military. For university, I don't want to work for free. I'm practically working for free for staff, right? As a researcher. I'm not costing him any money. That is very nice for researchers that don't have a lot of money. Maybe recommend Ruchan. Not saying that he is poor, I'm saying he has too many students. Tell him that high schoolers will not cost him a lot, and you will start see youngers join your group.
He has bad experience with high schoolers, so I don't think
Really?
he'll take those again.
Really?
Yeah.
Okay, tell me by the end of that, because I'm interested to understand what think I know what is the case that you're talking about. Yossi is also involved in that case, right?
Oh, really?
No.
Jesse is involved with everything.
Markers. That is the good marker. None of them are great. I have markers in my office, so if I would think that those markers are bad, I'll just go to office. Okay, so let's start from a nice stuff. So, how many students have you been in the lecture? 4?
5.
5. Can you skip the 5th one?
I don't know the name.
What?
I don't know the name.
Who is the 5th one?
We don't know.
I have
Her
absolute-
name?
Yes.
I have
Oh.
absolutely no idea.
Her name. Okay. Oh, I see that he did the boundary layers. What were written here, he did something like that. Sorry.
Yes.
So he solved the inner solution was around 1
Yes.
in that case, right?
I think it was
So-
the outer, but yes.
Yeah, it was outer. And
Outer.
and
Yeah, because it's the one
Yeah,
that.
it was between 0 to 1. So.
Yeah, okay.
there was also a middle solution. And it's 0. It's-
Okay, I think I know what is the example you showed.
You said that it's from the book.
Yes. Okay, I know what he showed you, but okay. That will not actually be the problem. That is actually good that he showed you those stuff, because that will give me more time, and that means that those stuff can appear, but they're not hard. Can appear in test. Wait. Just opening the right. So many windows. That is it. Yes. Here. Okay, so let's write the equation. Our tutorial last year were practically your lecture. It's pretty funny because our tutor were Schnell tutor for many years. So they didn't have any physical stuff or things like that. So I think they suffered from that problem, if you ask me. So the equation is that equation for a small amount of students, so it's good. It's also inhomogeneous, it doesn't matter. Homogeneity and those stuff in boundary layers doesn't matter. Right. So that is nonlinear, first indicator of boundary layers, right? Second indicator, the highest derivative has factor of epsilon. Okay, it's boundary layers. That's how you practically specify it.
You mean if it's not linear, we can't use WKB? And
You
that's
can
why
use
it's-
WKB, yeah, for or perturbation theory. It's practically the same for the case of. I tried to convince you that perturbation theory is also nice for nonlinear equations, and we did them actually, but they were in the form of L of y linear operator plus epsilon n y equal to 0. Non-linear operator that operates on y can be even a vector, and therefore each time what happened is you got equation that looks like that. Yn equal to, you do perturbation series on epsilon, and what you left with is yn minus 1 of, actually you have here epsilon to the, you have, okay, no, I think that's it. Yeah. Yes, I think that is how it's look, but we will get into that, I want, in the second half of the tutorial today. Something like that. But that's why they work, because you had linear operator operates on the function that you want to find, equal to function you already had with the epsilon. So that's why that works. And okay, and that equation. So yes, right. We should have only one, and it's y of 1 equal to 1 over a. So what do you do with that? Okay, I mean, you can try here to do boundary layers, perturbation theory, but it will not work that great because the linear operator is just multiplying by x and take the derivative and multiply by x, something that is strange. And what happened here, the nonlinear stuff where it depend only on y, and now it's depending on y tag also. So it's okay, the nonlinear term can also have tags, but it's different than what we did, and like you saw in its derivative affects the width by a little, right? Mm-hmm. Wait. It's 1, 2, 3, that eraser. Because when you transform it, the x, you get also factor of 1 over delta, right? For the inner solution. So derivative has some meaning with the width of the equation.
So now we're going to find the.
We do boundary layers. That were just introduction to why we want to do boundary layers. So what is the outer solution?
Just take epsilon to 0.
Yes. We will do only 0th order. We will not continue with that example to higher orders, but the next thing we will do will take that into account. So xy tag, yes, wait, yes, xy tag plus xy equal to e to the minus x, and then what we do is don't have any mistakes. Right? Okay, that will give us y tag plus y equal to x e 1 over x e to the minus x. And now you know the solution to that thing, right? And you know the solution to that. Actually, it will be nicer to write it. Yes, 1 over x, right? And that thing is just d e to the x y dx. smarter is
Integration factor.
what?
Integration factor.
Yeah, now we will do integration.
Yeah.
No, I think he meant that e to the x is integration.
Yes.
Yeah, maybe that is the name of that. I'm not sure.
רוני היה מוקלט.
I know. Okay, and now we got ln x e to the x plus c e to the minus x. Okay. First order ODE. Easy to solve, they are completely solvable. If we call that integration factor, yes, for that example, it is the integration factor. Yeah, and it's pretty much that's it. You can actually think about it as variation method, but applied to 1D. I'm sorry, to first order ODEs, right? Because what is variation method? You just take the homogeneous solution, multiplied but
yeah.
by inhomogeneous. That is something that is very good to do in everything that has ODs in it. I think he already has the intuition for that in the course. That thing is very useful, and when you will get to 2 timescales, you will see that something interesting that sometimes you do, that the 0th order, you assume it's constant time homogeneous solution. But for next order, sometimes if you want, for example, frequency shift and all of those stuff, you assume that that thing operates with epsilon to the alpha. Let's be more general with delta as a function of epsilon. It can be epsilon ln epsilon of x. So it's multiple scale method is practically taking that thing and put it as a function, and with that do perturbations. So let's get into the inner solution. What is the first thing that we will do in the inner?
Don't you need first to find C?
Find C? Yeah, I can find it here. You're right. I can find C. Just plug in
Well, basically 1, yes.
and C is. I can do it now or at the end.
Okay.
It doesn't matter. If you want, I will write. Right. So that is our inner solution. We will just plug t equal to x divided by delta, right? T is in the order of 1. So now what we're doing is like delta t minus epsilon y 1 over that will be divided by delta. Y dot is the name of the new variable, and delta t y e to the minus delta t. Okay, so what we're doing now, we just want things to not explode, okay? And what we will do is practically, okay, that with delta cancel, and now we will have only that term with delta, right? So what we will do is say delta and epsilon goes this same order. So now what we get, that thing is negligible, right? And what we have here is practically to first order of delta, leading order, yeah, leading solution. We get y dot equal to just a second, 1, right? I will just check that I am getting the right answers, right? And yes. and on the right track. Okay, so now it's a trick that you have to know that can appear on test, but it's not likely to appear, but it can. How do you solve that equation? For boundary layers in test, not in outside of test, it has to have analytical solution, the inner one. You can do estimations, but in test it's not likely to be the case, and you can ask Schnerb if it's okay, and if you don't have anything else, do that, sure, but for that case, what do you do? Because you can't separate variables,
Yes,
the first thing you want to try. The second thing is maybe that is a function of t of y. Look on that like it. Now y will be the variable and t will be the function. I know it's a little bit crazy, but let's try to apply it. Okay? What is y dot? Y dot is 1 over t prime y, right? Because you can one.
Yes.
Okay, nice. So now t of y minus y equal to t prime of y. Is that solvable? Yes, that is linear LD. Non-homogeneous one, but okay.
Oh, it's okay.
Yeah, it's completely okay. And what is the solution to it?
Multiply by the integration factor.
Which is e to the minus
Y.
y. Yes,
By the plus. No, minus.
e to the minus y. Yeah. We're not wrong. Nice trick, right?
Yeah.
When I saw that problem,
It's very
I had to bring it to here. I don't think it appeared in tests, but I think it did something similar in my test.
Should it be y e to the minus
Y e to the minus y?
Yeah, because you are changing the side of the equation and then you are
I
multiplying.
moved that side.
Then you are multiplying by.
Wait, I moved that minus y. Right. Yes?
No, I meant y times e.
Ah,
to the
yeah.
minus. Yes, okay.
Sure. And now, what is that thing?
It's the derivative of
The t of y e to the minus y divided by dy equal to minus y e to the minus y. Why this trick is not studied in ODE? We got that thing in our test in ODE, but never got that in actually class. You can ask Ronnie, he didn't like it. He gave us, and I were practically the only one that solved it. Not even Nathan solved it. So yeah. And from here you just do that thing. Where is the integral? I don't want to do it by myself. Yes. Very good. We get in now that this thing is just t equal to e to the y times c1 constant of integration plus y e to the minus y minus e to the minus y. Just integrating by parts the right side. Right? And by substitute what t is and plug it in, you get that inner solution y in is as a function of x. Now you say that this thing is x divided by epsilon, right? Because delta is epsilon. And now simplify it and all of those stuff, you can get that y in is just ln of x divided by c1 epsilon. Do you want me to do it? You think there is, wait,
But
yes,
how you have,
there is a,
how-
yes,
why
there is an
smaller
estimation here that, okay, yeah, there is an estimation here that practically y in the inner solution is very small because we multiply those stuff by epsilon, okay? That is what we will practically do. That can't be smaller than C1 does not depend on epsilon, right? Y can be small. And let's be more specific. We will write x equal to epsilon C1 e to the y. Here we will have epsilon y minus epsilon. The claim is that y will be much, e to the y will be much bigger than y, and practically we will have to check that assumption around 0, but that is the claim, okay? Let's just, for x that is much smaller than epsilon, okay? Is it clear what I'm trying to do?
The boundary condition is that what is
Wait, I will convince you better for it. I will find the right. Okay. It's multiplying everything. Thought for a second that it's. Okay, we will have to check that. Okay, by the end of the approximation. Okay, if it's valid or not. But what I will practically assume that this thing is approximately epsilon C1 e to the y. We will have to validate ourselves. Okay? Is it okay?
yeah, but I have a question.
Yes.
So usually for boundary layers we have a second order differential equation and
Yeah.
two
Yeah,
boundary
so
conditions.
now-
But now we have only one.
Because it's
And-
first order.
Yes, I know, but how we define in this case outer and inner solutions? How we match
same?
them? Or
The same. The matching is practically the same. It's not changing.
I mean, for outer and for inner solution, you
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 got
get-
only one constant. You get that will look like it. That is the outer. That is the inner. Right? That given one condition, right? One is for here. y0 is equal to one of the e. Okay? And the other condition is on y out. I'm sorry, you will have two constants. So you need two equations, right? You will get one for here and one for here. Do you agree with me? One constant you got from that condition, and one constant you get from matching condition. Right? So you have exactly this the unified solution.
Yeah, but somehow in outer solution you throw away constant or
What?
I think that what he's asking is usually we are solving this, let's say, between 0 to 1.
yes.
And now, should I get a specific value for x, which I'm solving the ODE, or I'm taking the inner solution to be to minus infinity, right? That's the question.
I'm not sure I understand your.
So why in outer solution you said that c is equal to 1? That is the question.
C
Because
is equal to 1.
in outer solution here. Yes,
Why I say that C is equal to 1?
because you have
I plugged in
Yes.
1, the ln that would be 0, and then you get C times e to the minus 1, and all of that's supposed to equal to 1 over e. Y of 1
yeah, but
equal to C divided by E equal to 1 over E, so C equal to 1.
yes, but a minute later you said that we using our boundary condition only for inner solution, not for outer solution. You said
So-
that.
Inner solution, not for outer solution.
Yes, you draw it basically.
Well.
You said that we're using boundary condition for inner solution, but here you use it for outer solution. It's a contradiction.
No, use it for outer solution. What is the problem? Okay.
In your sketch,
I
you
wrote-
wrote it that. Okay.
You're right. Yeah. I'm very confused for a second. Okay.
Thanks.
That is the only
Yes.
thing? Okay.
Are we always solving boundary layers in, how do you say, keta?
Section?
Yes, in section, let's say from 0 to 1. Or
No, you can solve it with infinity. For example, in Schrödinger equation, if you will try to apply it, one of the condition is that the wave function will decay.
it's plus minus
That is
infinity.
one boundary condition, right?
But this is because my boundary condition is in plus minus infinity. But let's say I will have a boundary condition in 0 and in 1. So my analysis will work also outside the section, or only inside between 0 to 1, which those are my boundary conditions.
The boundary condition for here you can think about them as initial conditions.
Okay.
If you have initial conditions, yes, it's applied for everywhere. If it will be valid everywhere, it's depend on the question, right? If you did approximation to get to that equation, sometimes it will not be valid outside, only in a small neighborhood around it. But it is global analysis, right? It's supposed to be valid everywhere. We will just look at that as a mathematical object. If we will solve it exactly and solve it with boundary layers, it's supposed to approximate each other. Suppose, okay? Okay, so that will be my assumption. Think about that if y is very small, okay? So that would be approximately 1, right? And that will be practically 0. That is assumption that we do. We will have to verify it. That is our. We will have to check the assumption. Okay. It is taken from the book, and there are not They're not explained it a lot, but okay. So just checking something. Okay. So the next thing that we will do is the matching. What will be the matching? Y in for x divided by epsilon less than 1, right? It has to be equal to y out for x is much bigger than epsilon. The oppositely for that example. What we will have to see here is, okay, where is my solution? Here. When that approaches infinity, that thing is negligible, but we're still left with that. I'm sorry, when that approach minus infinity, x is close to 0, e to the minus x is practically 1, right? But we have to keep that ln of x because it's exploding. So what will happen, that will be ln of x minus 1 plus 1 plus 1. We can't just say it's minus infinity, but we take the leading behavior. Okay? Sometimes if you will do higher order approximations, you will have to take more terms. So you will approximate e to the minus x as 1 minus x. Because you will have more constants to determine and match. And actually you will have what I will explain later. You will have some degrees of freedom that are not actually degrees of freedom for the perturbations. Okay, and the inner solution, it's there, will be ln of x minus ln of c1 epsilon. And now, look, it's beautiful. They both cancelling out. And what you get is c1 epsilon equal to 1 over e, because you have minus here, multiply everything with minus 1, and take it to the power of e. What you got is, okay, actually I said before that c1 is not depending on epsilon, so I practically lied, because it can depend on epsilon now when I'm thinking about that, because we want to find it, so I convert it to x, so I will have better, it will be easier for me to match, right? And when you do that, you actually introduce epsilon to the equation back, so it is dependent. Sorry for misleading. So that will be it. That is our C1. Now the only thing that needed to be done is now subtracting the what you count twice. That is exactly that thing, right? You count things twice. What you count twice?
ln x plus 1.
Ln x plus 1. So your final solution, let's write it. Our final solution will be by the way, just checking 5x. Yeah, okay. X is less than epsilon. Okay. Yeah. Okay, you can validate what we got here. Okay, just checking our assumption. What we got here for y inner. With that assumption, you can validate that. Just write that. You're supposed to get the right thing. Okay. And the y uniform of x is y in plus y out minus ln x plus 1. That is practically it, because that is the uniform solution, right? That is what you count twice. Do you agree with me? So it's a nice example that sometimes if things got rough and you try to do that, trying to take lead in order and all of those stuff. What I will do now, okay, maybe I will start with talking about Fredholm alternative, which we want to talk about. It's supposed to give you an idea of what do you do when you have more constants. You solving first order solution in perturbation theory. Sorry, zeroth order you got for second order ODE, 2 constants. Now solving the next order you will get another 2 constants. Do you remember?
Mm-hmm.
So how do you determine it? It's similar to what we did with the water waves. Let's present it generally. In general, we have y0 plus delta y1 plus, let's call that epsilon. Okay, let's do it perturbation series on epsilon just for the example. And then y0 plus epsilon y1. We get in that for zeroth order approximation, we'll do only for first order approximation, maybe I will start from zeroth order. What will be the zeroth order equation? y0, L y0 equal to 0. L is linear operator. We find 2 constants, let's call them A and B. Constants. Okay? You have the first homogeneous solution times constants plus constants times second homogeneous solution if it's second order ODE. And what you get for the next order, for y1, you will actually get y1 equal to that thing. Just take epsilon now because it's linear operator, and you're left with that thing. So here it will be the non-homogeneous solution plus 2 constants. Usually what I told you is the homogeneous solution here the same as the homogeneous solution for the next order. And you can see the pattern that it will go on and on. And therefore we can stack all those coefficients to what we had before. What I want to tell you now, it's practically it were a lie, but a good lie. Okay. I just want to introduce something that you will see in multiple scales. It's very quick, but it's practically what I want to show, that you have a condition that's determined. Let's think about y0 as a function of A and B. Okay. If you have zeta to be the solution of the conjugate of L, okay, that is a solution. What I'm saying is, now a nice trick will be multiplying everything by zeta, and they will get the condition. I will get something that will specify at least one of my solutions. But if it's second order ODE, I can take two zetas that are, their Vronsky is not zero, right? They will be independent of each other, right? Right?
But why can't you just say that y1 and y2 and all the other perturbations should be zero at the boundaries?
What I'm doing here is practically, okay, I will get to the point and then ask, okay? And now, that thing, and now just put everything here in an integral.
Okay.
Integral is our inner product, right? From minus infinity to whatever, specifically integral. And that thing is zero. Why that thing is zero?
So you can
They are
change.
orthogonal to each other.
No, it's practically like writing that thing,
Yes.
right? And then moving the L by the definition will be, but that is zero, so we get zero. So that thing is zero, that thing is zero, and you got specific integral. The integral is only a function of a and b, and it has to equal to zero. I did general thing here. It's called Feldon alternative, and it's specify and b. And what is nicer, if you have nth order equation, okay, that means you have let's call that from I equal to 1 to n, your solution. But you will have how many independent zetas? You will have zeta I, how many homogeneous solution to the conjugate one? Right, n, from 1 to n. So you have an equation like it. So, hey, what we did until now is wrong. That is, look like some sort of a paradox or something like that. By the way, that can be even, what I'm doing here is totally general. You can do it for even equations that you, ax vector, when you try to solve equation like it, plus epsilon and x vector equal to 0. When you try to solve matrix equation, the inner product will be just the transpose and things like that. Okay. So, what is the point here? The point here that the next order solutions will be now the non-determined one, the one that need to be determined by the initial conditions. Actually, what I'm trying to say that what we did, we're not wrong. We just said each time that, okay, we can call that those coefficients in general, or the zeroth order coefficient. When you're taking more and more terms, you will determine the last terms, right? But now I'm just calling that plus a known times some homogeneous solution, right? I have known one and I have something that is small. What I did is just calling that A and find with initial condition what that A is supposed to be. Okay, that's why we're not wrong, but sometimes this thing can be helpful, okay? When thinking about higher and higher order, and especially remember that for multiple scales stuff, because what happened is the next constant will be in order of epsilon, but it will be constant. So what you actually assume that for perturbations, like if it's OD on time, that will be the form of, you will assume all of the amplitude here, just a function of epsilon t, and if you will do approximation around 0, it will be like a of 0 plus epsilon a tag of epsilon t. And now finding that with the perturbation and Fredholm alternative, you can find another stuff that pops out. That has to be first order. That has to be function like that. Why? Because it's constant at first order. That is just something that I wanted to show because we had that a lot in our tutorial before, and each time I said something that is practically I waved my hand. I knew about that stuff, but I want to really read and give a nice explanation of what happened behind the scenes. Okay?
What's wrong with what we are usually doing? Like setting, let's say...
Just taking the non-homogeneous one, it's fine. That's what you should do. The non-homogeneous solution. Yes, right. And that's what I say, that even if you do it with Fredholm alternative, it's doing the same. The YH doesn't change.
Okay.
But each time you add epsilon times the amplitude, because the correction will be higher order, right?
Yes.
The only thing I'm saying is what we did is calling all of that A, that is a constant. And we find with initial condition what it's supposed to be, right? So it's not wrong.
No, I can see, but why should we do it? I mean, like this, what we are usually doing, at least what Schnell did is, so let's say we have some boundary conditions. So I'm deciding the boundary condition of y naught is the same boundary condition of y, and all the other perturbations are 0 in the boundaries. And that way I satisfy
All the other perturbations are 0 with the
and
boundaries.
that way I satisfy the boundary condition, and I have as many conditions as I need to determine all the constants.
Schnell did it on linear equations, right?
Yes.
Yes.
That is why. I just gave you because I gave examples that are not linear,
Okay.
those things appeared. In linear equations, you can do the same things, but just assume it's 0. On the other stuff, it's totally equivalent. Okay, but because here you had non-linear, I think that is why.
Okay.
Because it has some amplitude effect and all of those.
But it will be harder, or will it be wrong? Because I can't.
It
understand
will
why
not
it
be
will
wrong. You have many ways to approximate your solution.
Okay.
If it's valid approximately for the equation, and if it's approximates the solution of the equation and satisfies all boundary conditions, it's approximate solution. There are many approximate solutions.
Yes.
You saw there is many methods. That is just specifically, maybe it were better that we just send the notes of that because that's confusing. But I want to show that.
Okay.
And now let's do nicer stuff. Am I going too slow today, or it's okay? So, last thing, we'll just open. Okay, I will tell you what there is a couple of options of what we can do. Do you want to see a case of, that is the last thing we will do today, a case when there is needed a correction with LAN, okay?
Epsilon, non-epsilon.
Yeah, epsilon, LAN, epsilon, and things like that,
Well,
with higher order matched asymptotic stuff. I will present, it's written in the book, or I will show how to match solution when the inner one is in epsilon to the half series, and the outer one is in epsilon to the n, which is also interesting. When you try to match higher orders, I guess you never thought about that, but what for zeroth order it's not a problem, right? But for higher orders, it can appear that the delta here and the delta here are not the same.
You mean for different boundary conditions? I mean for
yeah.
inner different and for outer solutions?
You will have outer solution will be a power series of epsilon to the
Yes.
n, for example.
But
The inner solution will be n divided by 2.
we saw actually this in the lecture.
Which one is what?
Nadav showed this in the lecture. That
He showed you how to deal with those stuff?
Yeah.
Yes?
Yes.
Kessler didn't show last year, and I want just to... Okay, so if you showed that, you saw that, and you didn't show LAN,
No, we didn't saw that.
Yes.
so that stuff you know already, that you just have to introduce some another terms to
Yes.
that thing,
Yes.
and then start to do the perturbation, and it gets dumb a little bit, but because it's like introducing non-existing terms, but it's actually what it's catching the behavior with epsilon to the half, which is strange because you just introduced another term and all of those stuff. And were my approximation before were wrong? No. But is my approximation now is right? Yes. But that is strange thing that you can do and play with it, and that is practically the common trick that you do. That's why we talked a lot about how to get the delta. That's why I talked a lot on how to specify what is the width of our problem. I guess you talked with Schnell also about width.
Yes.
Today.
Yeah. Yeah. So we had the intuition from the polynomials I showed, right? Yeah, I thought it's nice, so it's good. So I will take the one with the LAN, right?
Yeah.
Because you saw it. There is the one which I want to show with multiple scales is actually also nice, but it's third order boundary layers, so that is the thing that were also special to it. But it's not a property of third order that those things messed up. It's something that happened when you try to do boundary layers for higher orders. So you did boundary layers to higher orders.
Not explicitly, just talked about that.
Yeah.
Okay.
But the different widths we did explicitly. So
But that effect usually appear for next orders. You did explicitly that? Not understanding what you did or not.
He said that this is actually the example from the book.
Okay. Is that here? Wait, so have you done that example? Epsilon y two tags plus xy tag minus xy equal to 0?
No.
Okay, good. So what I want to show here is just how you do trial and error in the right way. Okay, I will bring the calculations. You did with Nadav an example, but so the process is practically the same. But I just want to show you how you should behave in a test, right, or something like that, trial and error. How to do it schematically and not just start to guess and shooting everywhere. Where is my solution? Where is what I need to correct? Okay? So that is the equation. Let's do first y out, which is start with doing something wrong. Usually start with y inner, so you will get the width. So you will get, if you want couple orders of solutions to match, you will get that from y inner, right? By the way, I need to write what is my inner solution. y0 equal to 0, y1 equal to e. Yes? So, okay. So the first thing that we will try to do is approximate y out as an with just perturbations, right? Not anything spatial, because there is epsilon here. When you do perturbation theory, you will assume that is sum of epsilon. Why? I told you before that, okay, I have a lot of experience, so that's why I'm doing that. Because when you do perturbation theory, you try to catch in behavior, and practically that's what we do here. But we're not getting the small scale, the inner solution from that. So you can think about boundary layers as a correction to perturbation theory, and something that approximates, because what you will do in perturbation theory is assume that y solution is sum on n, epsilon to the n, y n. Right? What we will get here when you will also do it for that, it will be our y out actually, and when we will do it for y inner, you will get delta to the n, yn, and therefore you will do practically the same perturbation theory, but now when you will match them, you suppose to get something that is more accurate. Okay? Because for that we assume actually x is big and things are big, and for that we assume that something is small, and therefore we needed the match. And when you do next and next order, it's more likely that you will have to do tricks like that. And your uniform solution will be something that is not constant. Only for zeroth order you will get something that is constant. So you will just have to Taylor expand or seeing how the leading behaviors of it behaves practically. So let's continue. What I will tell you is when you will do that perturbation method, like you will get that y out is going like e to the x. Let's take that. E to the x minus epsilon e to the x ln x plus epsilon squared e to the x, and here you get something nasty, ln x squared minus 2 over x plus 1 over 2x squared plus 3 over 2. That's our solution to three first terms that you will get from straight up perturbation theory, right? So, and when you will try to approximate that to what will be the exact solution with numerics, it is a good approximation. I will tell you that the order of how that's called for epsilon equal to, let's see, for epsilon to be 1 over 100, the error of the leading term is 10 to the minus 2, so it's in order of epsilon, what you will expect. But for second order, it's something I will say pretty close to that. If I will, well, it's something between x 10 to the minus 2 to 10 to the minus 3, but tending to 10 to the minus 2. So it's not that great. It's not like it's now 10 to the minus 4, what you will expect from a perturbation series. So it's getting better and better, but slowly. So what we have to do is do it right, and maybe that will be a motivation to start boundary layers, because our approximation is not good enough. So first thing that we will do is defining our t as usual, okay, and finding the width of the equation. Minus delta ty equal to 0. So what is the width? Delta equal to epsilon to the half.
Square root.
Same thing. That is square root, right? Square root of epsilon. And what you will get for the inner solution, the base one, you will get, you want to take now a perturbation series, blah 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 blah, of our delta, and you will get that y0, let's denote that with capital Y for the inner solution, so we will not have to write each time inner. And you will get a to the integral of that t, yes. Yes. Let's denote that with s squared divided by 2. Yes. Okay. So now you can even start to see there is a pattern here which you can approximate that integral which you didn't study yet, but you know from other physics courses how to approximate integrals, right? A little bit. T is T, you know, it's something which is in order of 1, but T is x divided by epsilon to the half. So when epsilon tends to 0, that tends to infinity no matter what. So you can do a power series of epsilon to the half of that thing. Spoiler alert, it will not have to be power series of epsilon to the half, but you will see that when you will get to integrals. In that example, I will not show how to do the integral approximations, because you didn't study it yet, but the book actually assumes it. When you will study it, I think Schnell planning to do it by the last lecture, you will be able to recheck what I did here and check that my integrals approximation were valid. Spoiler, it's taken from the book, so it's approximation. You can do that with just intuition of you know how to approximate stuff. Will be nice, but that is practically it. And okay, and from the form of the equation, let's write that thing as, I will call that psi of x of s, okay? Just so I will not have to write it each time. A general form of the nth order the nth solution for that differential equation when you do the perturbation series. For the inner solution will be a n integral of let's do t psi of s ds plus integral, just checking, zero to t of psi s. Another variable will be u, okay? 1 over psi u du ds. That will be here y n minus 1 u. Whew. That you get for just general solution of the equation. Okay, trust me on that. You write the inner equation. What will be the inner equation? Okay, so practically that thing will be just y2 dots. That thing will be plus ty dot. That thing we will have epsilon to the half ty equal to 0, and you can maybe see the pattern here. I'm not sure. Wait, it's supposed to be with minus. But it's not the point. You do perturbation on epsilon to the half, and it's practically what I wrote before. It will be each time that term when you take the next order, that is y that depend only on yn minus 1. Okay, that is not the goal of it. I'm trying to speed things up. And for zeroth order approximation, just the zeroth order, let's do the matching. That is my matching, right? So now you want to approximate when what happened here, t goes to 0. When epsilon goes to 0, epsilon goes to 0, x equal to 0. Okay. Yeah. Okay. So zeroth order matching. What we will do is take epsilon to 0, x to 0, and t to infinity, right? So what will be y0?
Square root of
Pi divided by 2, yeah, right? A will be square root of pi divided by 2. What will be the other one? Where is it? Where you wrote it? Here. X goes to 0, so that will be 1. And nicely we find the first correction. So if you just want to do the zeroth order, nothing gets wrong, and you got your solution. You can even see here the uniform u unif will be 1, right? Constant, and you can unify the zeroth order. Okay, it's a better approximation for the zeroth order, but we want to get more and more accurate stuff, right? Obviously. So what we will do is practically taking that relation what we will do is taking that relation, do you see? And what I will do is just writing what y n dot equal to. Let's do it for y1. So y1 dot equal to a1 times e to the minus t squared divided by 2 plus e to the minus t squared 0 to t e to the s squared divided by 2, and now y0 of s, yes. Okay. So what? Just a second. When t goes to infinity, what we get, we just want to match our solution. We had already a nice form of our solution, so we get that y1 dot is approximately square root of pi divided by 2 a0 because of that thing. Okay? Do you see it? Dima? That vanishes, right?
Okay.
And what happened to it? It's practically integral approximation, but as first order, okay, what is, it's not very formal, but what I will say, it's like, assuming that is a constant, not that goes with that, and now just y0s. Why it's a good approximation for it? It's not a good explanation right now, but promise me intuitive. When you will study about integral approximation, it will be clearer. Okay? Just I want to show a point. I know I'm getting maybe too much into details, but want to just write it so later when you will see this, you will be able to understand what I did. So that and that, intuitively, that were right to do. Cancel out, okay? I know it's different. And then 0 to t of y0s is practically that thing. Okay? Or just believe me, that is the right form. And with that, y1 is approximately, for t approaches infinity, some pi divided by 2 a0 t plus integration constant. I just want to show what is the process of it. By the end, you will have to do that approximation. Right? Right? By the end, when you try to match more orders, you will have to do that approximation. And that is one method of doing it. Here you have integrals and all of those stuff. I know I didn't find anything better. Usually it's getting horrible and you usually have to dive into integrals, but we didn't do yet. So that is I spent something like 4 hours to find a better example, but I were not able to find. That's why I told you the LAN stuff pops out. Practically it looks like a regular boundary problem, but it's hiding it when you're trying to get into higher orders, horrible stuff. That's usually what happens. And with what I did, I will just write what is the approximations for next orders. You just use the recursive formula, and you will use your integration skills, which I know you still don't have because we did not cover it by now, but it's practically the same process. I can show you if that will satisfy you how to do that, but I don't think it's necessarily for now. And y2, the point of it is y2 has, by the way, the first problem, we got the width that is not right, right? So if you're a student that got that in test and start from the outer solution, that is bad. Now when you're trying to match in higher order approximation, we were able to match only the 0th order, but now for the first order there is no epsilon to the half here. You have to redo it. The next problem is actually what I will show you right now, that it is not enough. You did not go into details because next orders will introduce different scales, which is a surprise in that problem. So what we get is pi over 2 times a 0. It is 1. I don't know why they wrote it. It is 1. We got that. Oh, wait. That were for 0th order. Okay, I will write it like it's written in the book. T squared minus ln t plus half t squared and t to the minus. Okay. Plus C1 T plus C2 plus O of T to the third power. Yes? To the minus third. Why can I neglect T to the minus third when I'm trying to approximate y2? y2 is to the order of what? When I did it to the order of epsilon to the how would it go? To the 3/2, right? No, it's to the order of epsilon, and 1 over t when you move it to x, it's very negligible. Practically, just pass it because it's 3 divided by 2 epsilon divided by x to the third power, right? So that's why you were able to do that. That is just approximation for t approaches infinity. That is how you do it right. It involves integrals, which we did not cover yet. When I did the course for the first lecture or something like that, third lecture, I don't know why we did not cover it. But what is the problem? It erases here. What you got for the higher correction? What is approximately happening here? That is what I'm trying to say for something like 30 minutes with a lot of maybe unnecessary stuff that I maybe should just present it, but I don't know how to do it without the background. You got that long term when you try to approximate. That long term, when you substitute what is t, it will be x divided by our delta. It will be epsilon to the half. So you will get that is ln x minus half ln epsilon. Remember that y2 is multiplied by epsilon, by epsilon, so it's convergent, don't worry about this. But what it's introduced to our equation? Ln epsilon. So when you do y2 times epsilon, you have another perturbation. You can think about it like that. You will have terms plus something epsilon ln epsilon. And actually, if you will get to higher orders, you will have ln to the second power and a lot of those stuff. So you actually get a lot of stuff that is very strange, in my opinion. How do you fix it? Practically, you have to add a ln scale to your equation if you want to be more correct. You will you can try to do that with the book that will provide you the perturbations and do the matching. He gave to you to do the matching there, but what is appearing, that is the whole point of what I'm trying to say, that when you do next order, you have to be careful. What we have to do now in order to solve the equation, we have to erase what we've done until now, right? And add the other terms of the width that we got, sadly enough, because we missed them. Actually, it's something that appear only on y2, right? So you will have epsilon ln epsilon, but you will not have epsilon to the half ln epsilon. So I will say it's safe to stop after y1. If you want to get to higher orders, sometimes it can have things like that in your approximations, because you will do here. It's because that recursive here, that you just take the derivative with t, then you get rid of the integrals, first integrals, and then approximate. You have only one integral to approximate, and it will be much easier. But when you do it and you get terms that is in order of 1 over t or something like that, you got into a problem. That is, you have to say, Houston, we have a problem, and start the perturbation all over again because you got the width wrong. You will have just to add the epsilon ln epsilon and epsilon to the 3/2. You will have also ln epsilon and epsilon squared. You will have to introduce with that thing. Don't add also epsilon. Don't add in general something term that looks like epsilon to the n. And for that, do function n. Right? Because you can continue with that to infinity. That will still be a correction and correction. But actually, what you want to do is see what is the needed corrections, because you got that for the inner solution, right? That will be a perturbation in the inner solution. For the outer solution, we will just have to add them and then match the solutions. Okay, did you got the point, or are you were?
I think I missed it. But
Okay.
I hope I won't see this in test.
Yeah. It's horrible thing.
Yeah.
That's what I said. I'm pretty surprised that that's the other thing I said, that taking more orders, it is appearing, but how I did it in my test, Kessler asked us to do that, and I just take the y unit, did plus w, which is in order of epsilon, and find the solution without matching, he decreased my grade by 5 points. He took 5 points, but I will one of Don got not half the points. So out of 35, getting 30 for that, it's like I just took Y out. It's wrong. But I saw that problem and I was like, no. do that uniform. But the takeout here is just when you're trying to match, you got different scales, just add them to your perturbation. Okay? You got different scales, add them to your perturbation. Just add them without thinking. That is the only rule. You got here epsilon and epsilon, nice, add it to the outer solution. You got there epsilon to the 3 halves times ln epsilon to the 3, add it to the outer solution, just throw it. Add the term that with that order, and luckily I don't think there is simple example of that, so you will not get it in test, but most of the time, just to say to not scare you that much, it will be just a constant solution. It will be a phase. That's what happened here, right? That will give you a constant. You just have to match a constant, so you have to find a constant function. Yikes. Okay, that's it. I think that is a good place to stop. Sorry if we were a little bit confused.
Thank you.
Thank you.